Hello, I'm Rutvij, and today I'm going to be talking about improving device-independent randomness expansion rates using two-sided randomness. This work is already on arXiv and was done by me along with my collaborators and my supervisor, Roger. Right. So here is the poster of the work, and I hope to take you, I want to take you through different sections of this poster. So random numbers, as we all know, have a variety of uses for practical applications. However, it's often desired that these random numbers are private, that is, they are random to any party that tries to predict them. Now, obtaining such random numbers requires trusting of the devices that produce them, which is a major assumption. So for example, your manufacturer may be untrustworthy and may have tampered with your device, or you may have a faulty device to start with. Thus, we need device-independent protocols. In our work, we look at device-independent protocols of randomness expansion. The objective is to perform randomness expansion without trusting the inner workings of the devices. Instead, to certify randomness, the protocol requires performing a bell test. Now, for concerns that stem from experimental implementation as well as theoretical simplicity, we choose to focus only on the simplest non-trivial bell test called the CHSH test. Now, the CHSH test checks the violation of a two-input, two-output bell inequality called the CHSH inequality. This test is performed by two non-communicating parties, let's say Alice and Bob here, using two measurement devices and a shared quantum resource. In our work, we try to answer two important questions. First is, can we develop better protocols for device-independent randomness expansion compared to what is already available in the literature? And second is the way to compute rates for these protocols. Now, let's begin by understanding a typical protocol. So a typical protocol has three steps. The randomness generation step, here Alice and Bob perform repeated CHSH tests. They get output strings A and B for input strings X and Y. The second step is called the parameter estimation step, in which Alice and Bob calculate the CHSH score or the bell parameter using the input and output statistics in the generation step. If this bell parameter is too low, then they discard the data and abort the protocol. If the data is not discarded, then the outputs and inputs are sent through a randomness extractor to come up with a string of private random numbers. This final step is obviously called randomness extraction step. Now, as an example, let's look at the spot checking protocol, which is a well-studied protocol in the literature. In this protocol, along with the CHSH setup, we have a central random number generator. Now, when a round of a protocol begins, the central random number generator produces a bit T, which tells us whether or not a CHSH test is to be performed. The probability distribution for T is chosen such that the test rounds occur infrequently. Now, in a single round of the protocol, after generating T, it is supplied to Alice and Bob, instructing whether or not they should perform a CHSH test. If they do not have to perform a CHSH test, they just simply pass fixed inputs X equals 0 and Y equals 0 to obtain outputs A and B. Now, after the generation step is finished, Alice and Bob estimate the CHSH score using the statistics of only the test rounds. If this score is too low, then they discard the outputs and inputs. Otherwise, they run the outputs through a randomness extractor to get a string of random numbers. Now, in our work, we introduced and analyzed two different protocols, recycle inputs protocol and the bias inputs protocol. Let's look at the bias inputs protocol first. So in this protocol, unlike that in the spot checking protocol, there is no central random number generator, hence the locality loophole is closed. That's an advantage of it. But instead, Alice and Bob generate inputs using heavily biased random number generators. So this input randomness is no longer uniform. If after performing the generation step, they find the CHSH score satisfactory, they pass the outputs through a randomness extractor or abort the protocol otherwise. Now, until now, for the two protocols that we discussed, we have discarded input randomness. However, by assumption, we have input randomness, which is private. So therefore, you should include this in your randomness expansion if it is possible to keep your input randomness private after the protocol is finished. So we consider the recycle inputs protocol. In this protocol, Alice and Bob again perform repeated CHSH tests, but now with their inputs having uniform probability distribution. If they obtain the desired score, then they pass both outputs and inputs. So that now it's different. Crucially, you pass both outputs and inputs to a randomness extractor to generate your final string of random numbers. Now that we have discussed protocols at length, the only thing required for us is to compute the randomness rates for each protocol in the asymptotic limit as a function of the CHSH score. And once these asymptotic rates are obtained, we can find finite round rates using entropy accumulation theorem. Now, computing these rates using entropy accumulation theorem requires optimization of the single round one Neumann entropy over all possible strategies that your adversary may use. Therefore, computing these rates is a difficult non-convex optimization problem. In our work, we reduced this non-convex optimization problem to an optimization problem over 6 bounded real variables. Yet, the obtained simplification was hard to solve. So therefore, we solved this problem step by step. In the first step, we generated an upper bound of the rates by trying to numerically search for the best possible strategy that your eavesdropper can use. So what we did was, for each value of score, we guessed a random initial strategy, performed numerical minimization using standard algorithms to come up with the optimal strategy. We then repeated this more than 10 to the power 4 times for each score to get, and then reported the least amount of entropy obtained in all these minimizations. So as you can see, the rates we got are here, and each rate you can see the label for what protocol it is relevant to. Now, the results in the previous slides are still upper bounds, and hence they cannot be used for generating randomness in the protocols. So, but in 2 cases, we have been able to prove strict lower bounds for 2 entropies. One is relevant for DIQKD, and the other is relevant for randomness expansion, but more importantly for spot checking and bias inputs protocol. We show in our work of how to compute these rates, and as you can see, these rates are already an improvement compared to what is already available in the literature. We also, the method that we propose can be used to make these rates arbitrarily tight. As you can see again in these graphs, the obtained rates, the lower bounds are not very different from the upper bounds, and hence we conjecture that all the upper bounds in the previous slide are tight. Now, using entropy accumulation theorem and the results in the previous slides, we have been able to compute the randomness gain in all 3 protocols. These graphs show the gain in randomness in the protocol as a function of the CHSH score observed, and these graphs show the randomness rate gain as a function of the number of rounds for a fixed CHSH score. Now, we have optimized over all the bias parameters. Now, as you can see in all these 3 protocols, as the CHSH score increases, there is more randomness obtained. The shape of these graphs also resemble the shape of the rates in the previous slide, which should be expected. The amount of randomness expansion is highest in the spot checking protocol, in the recycled inputs protocol, followed by the spot checking protocol, followed by the bias inputs protocol. These results show that indeed using 2-sided rates for randomness expansion leads to superior protocols, therefore making these protocols more suitable for experimental implementation. So for example, in a recent experimental demonstration, it took about 19.2 hours to get a reasonable expansion. Assuming that it takes the same time to do a single bell test for our recycle inputs protocol, the use of our protocol would allow the same amount of expansion in as less as 60 seconds. So thank you for your attention. I hope to welcome you on my poster. Thanks again.